Welcome to today's paper reading. Today's paper is titled AutoScraper, a progressive understanding web agent for web scraper generation. This paper was published on the AR14 preprint by Wenhao Huang and colleagues from Shanghai Key Laboratory of Data Science, School of Computer Science, Fudan University. The abstract highlights the challenges in web scraping, particularly the limitations of existing methods such as wrappers-based approaches and the poor reusability of language agents in diverse web environments. To address these issues, the authors introduce AutoScraper, a novel two-stage framework that leverages the hierarchical structure of HTML and the similarity across different web pages to generate efficient web scrapers. Additionally, a new executability metric is proposed to better evaluate the performance of web scraper generation tasks. The effectiveness of the framework is demonstrated through comprehensive experiments involving multiple large language models, LLMs, and the work is made open source to encourage further research and application. Web scraping involves software automating the extraction of data from websites, typically using bots or web scrapers. This process is important for efficient data collection, which is crucial for market research and competitive analysis. Two main methods for automatic web information acquisition are wrapper-based and language agent-based. Wrapper-based methods require complex sequences of operations within customized rule-based functions, while language agent-based methods leverage natural language processing capabilities of large language models. Both methods face scalability issues. To address these shortcomings, the AutoScraper framework combines the strengths of both methods, aiming to enhance scalability and introduce a new evaluation metric for web scraper generation tasks. Figure 1 illustrates the comparison between wrapper-based methods, language agent-based methods, and AutoScraper. Wrapper-based methods, while reusable, struggle with new website structures, necessitating extensive human effort. Language agent-based methods, on the other hand, demonstrate superior adaptability but rely on limited, costly LLMs. AutoScraper aims to combine the strengths of both methods, enhancing reusability and performance in diverse web environments. Wrapper-based methods for web scraping include rule-based approaches, learning wrappers, and heuristic algorithms. These methods require significant human involvement, making them difficult to scale across multiple websites. Language agents leveraging large language models, LLMs, have emerged, such as chain of thought, reflection, and self-refine, which use LLM's self-reflection capabilities for iterative planning. However, these agents do not fully utilize web structural features. Current language agents aim to streamline the web environment and develop planning strategies, focusing on open-world web simulation environments. These methods, however, do not effectively exploit HTML structural similarities across web pages, leading to inefficiencies in repetitive operations. In this section, we first define the scraper generation task. Given a set of web pages on the same website and a predefined target attribute, the objective is to generate an executable rule to extract target information from all web pages. We use 3 datasets for this task: SWD, which includes 80 websites and 124,291 web pages; extended SWD, with 21 sites and 41 K-triples; and DS1, containing 166 annotated web pages from 30 websites. For evaluation, we adopt traditional metrics like precision, recall, and F1 score, but also introduce an executable evaluation to assess the generalizability and transferability of the action sequences. This evaluation categorizes results into 6 situations, focusing on the success rate of correct extraction. Table 1 provides an overview of the statistics for web scraping task benchmarks. It includes the number of cases, number case, the number of different extraction tasks, number task, and the total number of web pages, number web, for 3 datasets: SWD, extended SWD, and DS1. SWD has 320 cases, 32 tasks, and 32,000 web pages. Extended SWD has 294 cases, 221 tasks, and 29,400 web pages. DS1 has 83 cases, 11 tasks, and 186 web pages. These statistics highlight the scale and diversity of the datasets used for evaluating web scraping tasks. Figure 2 illustrates the AutoScraper framework, which consists of two main phases: progressive generation and synthesis. The progressive generation phase utilizes the hierarchical structure of HTML to progressively understand and prune the web page, making it easier for the large language model, LLM, to generate executable web scrapers. The synthesis phase then integrates multiple scrapers generated from different web pages to produce a cohesive, website-specific scraper that functions universally within that site. This approach addresses the challenges of long HTML documents and reusability across various web pages, enhancing the efficiency and scalability of web scraping tasks. The AutoScraper framework is designed to generate a scraper for extracting specific information from semi-structured HTML. It consists of two main phases: progressive generation and synthesis. In the progressive generation phase, the framework utilizes the hierarchical structure of web pages to generate an action sequence, denoted as ASEC, which consists of a series of XPath expressions. This sequence is generated from a set of seed web pages and is used to prune the web page and extract the target element value. The progressive generation phase also employs a traversal strategy involving top-down and step-back operations to refine the DOM tree and improve the performance of the generation process. In the synthesis phase, the framework enhances the reusability of the action sequence by selecting multiple seed web pages and generating different action sequences for each, ultimately choosing the sequence that can extract all target information across the web pages. The experiment aims to answer three key questions. Firstly, whether AutoScraper can outperform existing state-of-the-art scraper generation methods. Secondly, how the AutoScraper framework enhances the performance of the scraper generation task. Thirdly, whether AutoScraper meets the criteria for accuracy and efficiency in web scraping tasks. The experiment was conducted using 8 different large language models, including both closed-source models like GPT 3.5 Turbo and open-source models like CodeLlama 34B, all under zero-shot settings. The models were tested on 3 datasets: SWD, Extended SWD, and DS1. Evaluation metrics included correct and unexecutable ratios, as well as precision, recall, and F1 scores, both in executable and information extraction evaluations. The results were compared against baseline methods such as COT and reflection. Table 2 presents the executable evaluation and IE evaluation metrics for various large language models, LLMs, across 3 datasets: SWD, Extended SWD, and DS1. The metrics include correct, unexecutable, precision, recall, and F1 score, with the best performing scores highlighted in bold. This table helps in understanding the performance of different LLMs within the context of web scraping frameworks, providing a comprehensive view of their capabilities in extracting and evaluating information from web pages. Table 3 presents the results of an ablation study on AutoScraper, focusing on the correct and unexecutable metrics derived from the executive evaluation, as well as the F1 score from the IE evaluation. These metrics are reported using the SWD dataset, providing insights into the performance and effectiveness of AutoScraper's components. Table 4 compares the direct extraction performance of various large language models, LLMs, with that of AutoScraper on the SWD dataset. It reveals that, except for GPT-4 Turbo, all other LLMs exhibit superior extraction performance compared to AutoScraper in direct extraction settings. However, as LLMs improve, the performance gap between the two methods diminishes. This suggests that while LLMs like Phi-3 Medium can effectively understand web page content, they struggle with comprehending web page structures. Conversely, AutoScraper, when combined with the best current LLMs, already demonstrates superior extraction performance and is expected to further improve as LLMs continue to advance. Figure 3 illustrates the performance of AutoScraper as the number of seed websites varies within the SWD dataset. The results indicate that the performance of the scraper is influenced by the quantity of seed websites, with implications for the stability and generalization capabilities of the generated scraper. This experiment highlights the importance of seed website selection in optimizing the effectiveness of AutoScraper. In this discussion, we explore several key aspects of AutoScraper. Firstly, we compare AutoScraper with direct extraction methods using large language models, LLMs. The results indicate that while LLMs like Phi-3 Medium perform well in understanding web page content, they struggle with comprehending web page structures. However, as LLMs improve, the performance gap narrows, suggesting that combining AutoScraper with the best LLMs can yield superior extraction performance. Secondly, we compare AutoScraper with supervised baseline models and web information extraction tasks. Despite being in zero-shot settings, AutoScraper outperforms these models, demonstrating that LLMs can surpass supervised learning methods in certain tasks. Lastly, we analyze the efficiency of AutoScraper. While generating a wrapper takes more time initially, the extraction efficiency for subsequent web pages is significantly improved. Our analysis shows that AutoScraper becomes more efficient with as few as 19.5 pages on average, making it suitable for large-scale web information extraction scenarios. Table 5 presents a comparison of the extraction performance, measured by F1 scores, of 5 baseline models against our method, AutoScraper combined with GPT-4 Turbo, on the SWD dataset. The baseline models, which include RenderFull, Freedom, SimDLM, MarkupBase, and WebFormer, were each trained on one seed site. Despite being in a zero-shot setting, AutoScraper outperformed all baseline models, demonstrating that with an appropriate framework, large language models can surpass supervised learning methods in certain web information extraction tasks. The F1 scores for the models range from 82.32 to 88.69, with AutoScraper plus GPT-4 Turbo achieving the highest score of 88.69. Table 6 presents a detailed analysis of the time efficiency of GPT-4 Turbo in web information extraction tasks. The table highlights that the threshold of page numbers needed for AutoScraper to become more efficient is 19.5 on average. This is significantly lower than the average number of web pages per site in the SWD dataset. The comparison between the total extraction times with and without wrapper generation, T1 and T2, shows that generating a wrapper initially takes more time but significantly improves the extraction efficiency of subsequent web pages. This efficiency improvement is crucial for large-scale web information extraction scenarios. In this paper, the authors introduced the AutoScraper framework, which is designed to improve the reusability of language agent-based frameworks by combining large language models, LLMs, with scrapers. The framework operates in two phases: progressive generation and synthesis, which together generate a more stable and executable action sequence. Experimental results show that AutoScraper outperforms current state-of-the-art baselines and scraper generation tasks. However, the framework has limitations. It is primarily effective for information extraction tasks on vertical web pages and relies heavily on the performance of the underlying LLMs. Additionally, it has limited transferability to other web environments such as Mind2Web and WebArena. Future research will focus on enhancing the ability of LLMs to understand HTML, including the collection of training corpora and refining training strategies. Thank you for watching.